right? I had to pause it. Let's see, effects, options. My color. I'm having another problem here that my picture doesn't show up in my screen capture software. Let me see if I can fix that. Oh boy, sometimes those software, they don't behave the way they're supposed to. It's very frustrating. Help suit. Okay. Home. Webcam. Screen capture. Webcam. Record the screen. Yeah, he doesn't let me. Okay. Doesn't look like I'm gonna be able to get my picture there in the software. Okay, you won't be able to see me in the recording software, okay? In the video. I'll try to fix it next time. I gotta call those guys who sold me the software. Recordings, let's see here. Effects, options, audio options, schedule. This webcam. Let's see here. Cancel. Continue recording. Be stopped. Are you sure? No. Cancel it. Video options. Select recording window. Yeah. Okay. Won't be able to see me there. But let's continue this way. Let's take a look at the handout. The window to the right should appear. Now click on the capacitance square. Don't forget to check the box first, right? No, not this one, it's this one. Plate charges, meters. Click capacitance square so you can measure the capacitance. Check box. Slide the voltage to 1.5 volts. Here you go. See that? When I slide the voltage, it becomes positively charged here, negatively. If I decrease to 0, no charge whatsoever, right? If I go on the other direction, the direction of the charges is inverted. Positive at the bottom, negative at the top. Okay? Like that. Or you can disconnect the battery too, right? Here you go, you can disconnect the battery. When you disconnect the battery, the capacitor remains charged. Okay? Just like in this capacitor, we cannot see the charges in this device. Here you go. See, this one positive, charged. Okay? We cannot see, but we are able to measure. Right now, my capacitor is charged. If I have a multimeter here, I would be able to show you that this capacitor is carrying a given voltage, a given amount of voltage, which would be around 9 volts if my battery is fully charged. Let's connect the battery again. Here you go. You don't have to hold it. You don't have to keep it connected all the time. What we want here, this one. Here you go. Slide the voltage, we did that. Connect the voltmeter to the capacitor. Okay, we do have a voltmeter. In order to use the voltmeter, you have to check the box here. See that? The voltmeter shows up. Let me show you a voltmeter that I have. This is a real life device, okay? Here you go, I got it. One of my box of toys. Some of you must be already familiar with that, right? Is anybody familiar with multimeters already? Anybody has worked with multimeters before? I want to hear from you. If you haven't worked, feel free also to say I haven't worked with. Every now and then I meet a student that tell me all sorts of things that they do with their car, you know? It's amazing. There are some students out there, those guys are so advanced that they know more than I do, you know? A few semesters ago, I met this student in physics 122, and he told me that he was working in his car, and he was programming his car to do certain things, this and that, you know? I look at him, do you do that? Do you know how to do that with your car? I guess, oh yes, I do that all the time. Huh? And then one day I go visit this student. I'm riding with his car there, a nice BMW. And he's telling me, oh yeah, by the way, I have the cell phone here. I hooked up my cell phone to my car and I can monitor all sorts of parameters of my car, you know? So every now and then we get students like that. And the guy was telling me that he's improving the performance of the car. And he didn't understand why the manufacturer of the car didn't make this car available with a better performance for the consumers, for its clients. And this guy was improving the fuel consumption of the car, you know, a car that he bought out there. It's amazing, you know. Some students they go into that. And another day I met another student too. This guy that I'm talking about is from CSU, by the way. He's going to medical school. He must be in his 20s, early 20s. He's already knows stuff that I don't know. And then there was this other guy from LA Harbor College. He also likes to work with cars. And he told me he does consulting for auto manufacturers, you know. He goes, so he plays with cars as well. He goes to racetracks and he races with his car. He knows how the car works and all that stuff. And he does consulting for an auto company. Every now and then we find students like that. Anybody knows how to use multimeters, by the way? All those guys, you know, they know how to use multimeters. I don't even have to ask them. So anybody want to share any experience that you have like that? You go. No, I don't hear anything. So I presume that you haven't played this multimeters. Here's a real life multimeter. Let me stop the sharing again. You go. Real life multimeter. This one I bought for $15. Okay. And what you have there in your screen is also a multimeter that looks like this device. There are a bunch of multimeters in the market. They vary in price anywhere between $10 and $3,000, okay? So, depending on the capability of the multimeter. And so what we are going to do in this simulation, we are going to measure the voltage of the capacitor. But before we measure the voltage of the capacitor, let me show you how we do that in real life. Before we measure the voltage of the capacitor here in the simulation, let me show you how we do that in real life with my own multimeter. Voltage is a measure of the amount of energy that a given device carries, the amount of electrical energy that a given device carries. Okay? That's how you should think in terms of voltage. The higher the voltage, the more energy a given device carries. Let's see here. I'm suspecting. Bear with me a few minutes. I think I got the wrong cables. Let me see if the cable is going to work or not. If it doesn't work, I switch to my other multimeter. I have another multimeter here. This one was more expensive because it has more capabilities. Okay, this one cost me $15. This one cost me $300. Several years ago I bought, maybe 10 years ago. Okay, the cheaper one was made in China. And I was looking for a very cheap multimeter in the market. I found it in the internet. And when I tried to buy something like that again, I couldn't find it the same model for $15. The Chinese had raised the price of the multimeter from $15 to $30. Now, if you want to buy something like that, It's gonna cost you $30 now. But they improved on the appearance of the device, okay? They raised the price, but they also improved on the appearance of the device. So what I'm gonna do, I'm gonna set this guy to measure voltage. Voltage, oh, right now, voltage, see the dial here? This dial is set to measure voltage. And let's see what is the voltage in the battery first. Hopefully my probes are working properly. Oh yeah, it's working properly, that's good. So it's not a 9 volt battery. This battery became discharged, okay? See, now it's 515 volts, 5.15 volts. This battery is not fully charged. 5.15 volts. Now let's see what's the charge, what's the voltage of my capacitor. Most likely I have already lost some charges in this capacitor. I'm gonna connect the ends of the probe to the ends of the capacitor. A little bit tricky here. You go positive to positive, negative. Oh, it's not positive. Okay, so my capacitor has lost some voltage. Now it's 1.25. While it was sitting down there, the capacitor lost some charge, okay? Ideally, a capacitor shouldn't lose any charge, but we're talking about ideally, right? In practice, capacitors are not fully insulated, 100% insulated. Now, right now, the capacitor must have gone back to 5 volts. Let me see if I can show. Yeah, you have to believe me, okay? You have to trust me. I cannot hold it in front of the camera. It will be too complicated for me to hold in front of the camera. So let's measure it again. I accidentally touched both wires. I guess it became discharged. Yeah, I accidentally discharged the capacitor. Let's charge it again. I accidentally touched one of the legs of the capacitor to the other. Right now it should be 5 volts. Simple procedure, right? If it's not 5 volts, oops, something else must going on. Positive of the. Oh boy, I still have 1 volt here. What's going on? Let's try it again. It's possible that I accidentally discharged my capacitor again. Okay, so here we go. Positive is positive. See, the tip here is positive. The tip of the battery is positive. This other one here is the negative terminal. Let's see if we got it now. Just the mere fact that I'm touching the terminal, it's possible that I'm discharging it as well. Touching the terminal with my fingers. Okay, now I see 5.1 volts. Okay, let me see if I can show that. It's going to be a little bit difficult because I have only 2 hands here with me. But if you're seeing what I am seeing, it's 5.08 volts. Keep on oscillating between 0.4 and 0.8, okay? So right now this capacitor is charged, and that's what we're going to do here in this experiment. Let me start sharing the screen again. Here you go. Okay, so here you go. The black terminal of the multimeter corresponds to the negative of the multimeter. The red terminal multimeter corresponds to the positive of the multimeter, okay? So what do? We touch the probe of the multimeter, just like this probe here that you're seeing. Right? Just like this probe here that you're seeing. To the negative, and the red probe to the positive. Remember that you can disconnect the battery if you want. And what we get here in the multimeter, you get 1.5 volts. In my case, it was not 1.5 volts, it's just more. It was 5 volts. Okay, so this simulation that you see here correspond to real life, correspond to how we perform the experiments in real life. Let's see if my capacitor has discharged or not, has been discharged or not. I'm going to do the following. I'm going to put my camera here in my tripod, and hopefully we'll be able, oh gosh, I can't. Or maybe I can. Okay, good. Let's see. Let me stop sharing the screen. Okay, here you go. My hand is in there. I'm going to image my multimeter. Okay, it's starting to get messy. My table multimeter right in here, 0 volts, right? Here you go. My journal, notebook, put aside. Let's measure the electric potential here. Let's see if hopefully my capacitor didn't get discharged. Negative is the negative. Oh, moving. Positive with positive. Yeah, it's becoming discharged little by little. Last time I checked, it was around 5.05. It is losing charge, but it's losing charge very slowly. No capacitor is an ideal capacitor. Okay. Now I am going to, again, I'm going to discharge my capacitor. Just like I did before, I'm going to touch this terminal with the other terminal. Okay. The negative charges are going to combine with the positive charges. The capacitor is going to become discharged. I'm going to measure the electric potential between those wires again, and you're going to see that it's no longer going to be 4 volts. It's going to be 0 volts. See that? 0.03 volts. Oscillating a little bit. I'm going to, here you go. I'm going to show you, now I'm going to measure again the battery. How many volts I have in my battery, right? Negative, oh gosh, and positive, here you go. See, this battery was supposed to be 9 volts, but it's becoming discharged. It has only 5.15 volts. That's okay, I still can use it. Okay, and then I'm going to charge again, recharge my capacitor. My hand is in the way, huh? Here you go. Charging the capacitor. Positive terminal of the capacitor to the positive of the battery. Negative terminal to the negative. Right now we should have a charged capacitor. Red probe to positive. Okay, here you go. Red probe to positive. Black probe to negative. 5.12 volts. See that? I can keep on doing that over and over again. I'm always going to get the right result. And now I'm going to discharge again. I'm going to put my 2 hands. Let's see if it discharged. I'm going to connect the 2 wires with my hand, with my finger. Okay? And let's see if I discharge the capacitor. We usually discharge it, but sometimes we don't. Let's see. Oh yeah, it didn't discharge. So my hand is not a good conductor. The capacitor is still holding it. My hand is more like a dielectric, right? My hands more, my fingers more like a dielectric. Now I'm gonna put my keys here. They are all made of metal. They're conducting devices, right? I am supposed to discharge the capacitor when I touch those 2 terminals of the capacitor here. I'm supposed to discharge. Let's see if it gets discharged or not. Here you go. Positive with positive, negative with negative. See? Discharged. Because the metals in my key, they are good conductors. Okay? So that's a little demonstration in real life, a real life demonstration. I'm gonna remove my camera, put it elsewhere. Tripod, go get there. Let's see, I cannot get this guy to fit there. Where's that? I get it right now. Okay, I'm back here. Let's share the screen again and let's continue with the activity. Let's see what he asks us to do. Right? Using the arrows to control the separation. Okay, so what are you what you have to know? I didn't cover that in my notes, and we are going to cover that in the lecture as well. But let's cover that again. Here, let's go cover that. Is that the capacitance of this device depends on the distance between the plates and the area of the plate. The larger the separation between the plates, the lower the capacitance that we have. The larger the area of the capacitor, the larger the capacitance is. What you see right in here, multiplying those two quantities, depends on that constant that you saw before, the electrostatic constant. That large number, 9 times 10 to the 9, remember? 1 divided by 4 pi k. Okay? So what we're going to do, we're going to vary the distance between the plates in this simulation, and we are going to measure the capacitance. Not this one right here. Nope. Here you go. Slide the voltage using the arrows to control the separation of the plate and the plate area. Take data for a variety of values, okay? So here you go. See that? A table. Separation D, plate area A, area divided by separation, and capacitance. That's what we're going to do. So let's go ahead and get your spreadsheet. Get your spreadsheet here. Zoom in. Let's see. Oh, here you go. See the positive. We generate a new sheet. We label it capacitance. For mine, right? You can do the same. Here you go. Zoom in a little bit so you folks can see all of that more easily. What do I like to do? I like to freeze the panes of my Excel spreadsheet. Let's freeze it right here instead. Unfreeze the pane, freeze pane. Here you go. And then going back, separation D. Okay, D. What's the unit that he's using? Nope, not this one. In millimeters. Ready? Area. What's the unit that he's using? Millimeter square. Oh, by the way, don't put in millimeters. Let's put in meters instead. We convert that from millimeters to meters, okay? The area should be in meters square. Let's use all the SI, the real SI units, the important SI units. There's a reason for that. What else? He asking the A divided by B. I'm going to put the unit in parentheses. I'm not going to write down the units. You got to figure out yourself. And what I'm going to do, I'm going to measure the capacitance. Okay, plate charge. Yeah, see that? We have a device that measures capacitance. And by the way, not every multimeter has this capability, okay? But some multimeters can measure capacitance. This $15 multimeter of mine, it does have a capacitance meter right in here. Okay, not everyone has, by the way. I was lucky to find this $15 device that measures capacitance as well. Not everyone, but not everyone has this capability, okay? And that's what you have here in your simulation. You can measure the capacitance of the device as well. If I uncheck, right, capacitance is going to disappear. Check again. Plate charge, see that? There's no plate charge there. Oh yeah, there is. Why it says no plate charge? Interesting. Huh. Interesting. Okay, I gotta start all over again. Reset it all. Yeah, let's reset it. Okay, so again, if you missed anything, put 1.5 volts here to charge the capacitor. We can disconnect the battery. Okay, so we do have some charge. You can see that this dial is a little bit more right up on the top. Put the capacitance in there, put the voltmeter there. And when I'm just repeating what we did. When I put the probes in there, we get 1.5 volts. Oh, wait a minute. I gotta share the screen. Thank you. Here you go. Okay. The voltage in this plate is 1.5 volts. Okay, so here you go. At this moment, the separation is 10 millimeters. 10 millimeters, you divide by 1,000, you get that in meters. Plate area is 100 millimeters square. You gotta convert that. You know what? Let's go back here to it's better if you leave that in millimeters, okay? Leave that in millimeters. Otherwise, it's gonna be a little bit complicated to convert. Yeah, leave in millimeters for now. And then, here you go. So what we are going to do? We start with 10 millimeters. And we start with 100 millimeters square. A divided by D is what? A divided by D is going to be 10. It's going to be 10 millimeters, the unit. And then you measure the capacitance. Okay, here you go. Now click the capacitance, take the data for a variety of values. Okay, so the capacitance that we have here is 0.89 times 10 to minus 13 Faraday. Okay, so go ahead, log in your spreadsheet. 0.89 E what? 10 to minus what? 10 to minus 13. Okay, and don't forget it's a Faraday. And let's see, now you gotta collect this data for different values. How many? 8. Total 8 is asking. 1, 2, 3, 4, 5, 6, 7, 8. I do not know whether there is a line here. Okay, so let's see what distances are available. Okay, let's see if we can go any further. No, it looks like 10 millimeters is the largest one. Hey, wait a minute. Okay, you gotta click on the arrow. Okay, 10 millimeters is the largest one. If we how close can we go? Let's see how close we can go. Yeah, that's the closest we can go. Okay? From 5 to 10. Okay? So let's take the capacitance. Yep, capacitance at 10. Not at 10, at 5 millimeters separation. We get 1.77 times 10 to minus 13. 1.77 times 10 to minus 13, right? Yeah, Faraday. And that's 5 millimeters, 100 square millimeters. Okay, A divided by D is going to be 20 now. Don't forget to put the unit there. What else did he ask? Let's see. Using the arrows to control the separation in the plate area, take data for a variety of values. Okay, let's get one more. Let's see. I'm gonna put 6 millimeters. We want 8, right? So we need 6 more. We can do 6 millimeters. Yeah, 6 millimeters. 1.47 times 10 to minus 13. I'm gonna put my spreadsheet side by side my software, my simulation software. Six millimeters. I'm not gonna change the area yet. 1.47 times 10 to minus 13. Let's go 7 millimeters now. So go 7, 8, 9, right? I'm not going to change the area. 7 is 1.26, e to minus 13, 8. Whoa. It doesn't look like I can get 8. It's okay, if you cannot get 8, I'm going to put 8.1 here. 1.1 times, 1.1 times to minus 13. Oh gosh. Nine. 8.9. I'm not going to struggle with that. 8.9. 1 times 10 to minus 13. E minus 13. Oh, interesting. You gotta put a number in there. Okay. Can we get more? We need 2 more data points. Let's see if I can get 9.5. 9.5. Yeah. 9.5. 0.93 E minus 13. We want 8, right? 1, 2, 3, 4, 5, 6, 7. Let's get another one. I'm going to get 8.5. Whoa. I can't get it quite there. 8.7. Let's do 8.7. For some reason I cannot get that. Next, 1.02 E minus 13. Everybody's got that? Okay, now I have all the points. Why he's asked for A divided by D? There's a reason for that. Because the formula for the capacitance, depends on A divided by D, okay? notes. See? The formula for the capacitance depends on A divided by D. It goes linearly with this ratio. So, don't forget to put the units. Now click on Dielectric tab at the top. And now we're going to put a dielectric there inside. Okay? The formula that you see here, let's go back to the equation for the capacitance. Okay. This is not the whole story of the formula. This is not. This is the equation only for the capacitance when you have air in between the plates. Okay, let's put that here. This is the equation. This is the equation for the capacitance of a capacitor with air in between the plates. Okay. However, if you put a different material there, can be glass, can be paper, can be mica, right? Mica. The equation changes. The more generic equation is a kappa that goes in front of the epsilon naught. Okay, and this kappa has a name. It's called is the dielectric constant. Okay. With vacuum or air between the plates, the kappa, the dielectric constant, is equal to 1. And what we're going to do, we're going to put the different dielectrics there and see what, how the capacitance changes. Let's do that before we go into a break. Okay, now click the dielectric tab at the top. Dielectric tab, let's see, dielectric. Oh, dielectric right in here. Okay, and then we can insert the dielectric here. Okay. Between the plates, we're gonna do a sandwich of dielectric. We can have all sorts of dielectric. Okay, see Teflon here, paper, glass, costume, you know. You can change the dielectric constant from 1 to 5. Let's take a look at the dielectric constant in Wikipedia. Wikipedia, dielectric constant. Wikipedia. Wikipedia. Let's see if they have a table here. There is that. You go. Oh, it doesn't have it. Let's see. Table of dielectric constants. Table of dielectric constants. Okay, dielectric constant is also called relative permittivity. Okay, that's another. Here you go. Let's see another name. Relative permittivity or dielectric constant. Okay, for the air and vacuum is close to 1. Air is 1, close to 1, right? It's a little bit more than 1. For the air, by definition, is 1. Teflon is 2.1, just like we saw there in the simulation, right? Polyethylene is 2.25, polyimide 3.4, and so on. Let's see if we have, oh yeah, we have mica here. 3 to 6 has a very high dielectric constant. Anywhere between 3 to 6, depending on the mica. Sapphire. Hey, do you know sapphire? A precious stone, anywhere between 8.9 and 11.1. Concrete, Pyrex, the glass, the type of glass, neoprene, rubber, blah blah blah, all sorts of ammonia, water. Water, 87.9, depending on the temperature of the water, okay? If it's water at 0 degrees C, it's 87.9. If it's at 20 degrees C, it's 80.2. If it's boiling water, it's 55.5. Okay? So depends how you sandwich your capacitor. You're going to get a different capacitance. But it's still going to depend on the area and then the distance between the plate. But then it's going to depend on the third parameter, that is the dielectric constant of the material. So let's do another. He's going to do, let's see here. Now click on the dielectric tab at the top, slide the dielectric in between the two plates, adjust the plate area, and separation again to take 10 new data. He said 10 new data points. He didn't say 10 new data points here. Oh, okay, he didn't say 10 data points, but he said 10 data points here. Let's do 10 data points now. Haha, he said 10 data points, but he he put only 8 here, right? Those guys are so funny. Remember I told you we have a bunch of mistakes here? Okay, so you want to write down the value of the dielectric constant. It has no units. The dielectric constant is a unitless quantity. Okay, let's do 8. No need to do 10. You know what? 250. Let's do that. Before we start that, let's have our break. Okay, and then we come back here. Let's see. That's the equation. Break. 2:50 p.m. to 3:05 p.m. Okay? I'm going to stop sharing the screen and I'm going to, no, let's see, mute myself, turn off my video. I'm not going to turn off my video because I don't want to lose. Okay, I'm going to just mute myself. So I see you soon. Okay, I'm back here. So let's go back to our table. We are going to perform the same experiment, but now we are going to change the dielectric constant that goes in between the plates. Let's get this table nicer. Here we go. Those. He didn't ask us to plot any graphs yet, right? Yeah, he didn't ask us to plot any graphs yet, but he will. I'm quite sure he will. Analysis, what do you see? From there. Yeah, that's right. Eventually he's going to ask you to plot the. Okay, so here go. So you're going to insert 3 different dielectrics, and you're going to vary the plate separation. Let's do only 8 data points. Let's not do 10, you know. What the heck here? 8 data points. Double strike, here you go. Let 3 different dielectric constants. Let's see which one I'm going to use. They're going to use Teflon, paper, and glass. Okay? Let's start with Teflon. Teflon, we go ahead and insert our block of Teflon here. Oh, don't forget to increase the electric charges. Okay, so what happens when we insert the Teflon? Let me show you exactly what happens when we insert the Teflon here. Here you go, here, see the symbol of the capacitor. Let me see if I have a good illustration for you. Very simple one. Yeah, no. Oh yeah, here you go, right in here. So here you go, vacuum between the plates of the capacitor, right? That's how we started. One plate is negatively charged, the other one is positively charged. Okay, there is a force between them and an electric field. This red line is an electric field, something that we're going to cover. We didn't cover that in the lab yet. If we put a piece of cardboard or a piece of glass or a piece of plastic, a dielectric in general, what happens there inside? Okay, let me tell you what happens there inside. This positive plate here of my capacitor is going to attract the negative charges in the dielectric. Okay? It's going to separate the negative charges to the positive from the positive charges. That's what's going to happen. Okay? And then we have, at a microscopic level, we're going to have something like that.
Professor?
Oh, yeah, I didn't share the screen. Thank you.
Yeah.
Oh, boy. Thank you. Don't feel ashamed to. Supposed to see. Yeah. Okay, so here you go. Let's go back to the. Right, let's do that again. Plates, air or vacuum there in between. Those 2 plates are attracting one another, but because I'm keeping them fixed, they are not gonna crash against each other, right? We do have what we call an electric field there. But when we put a piece of cardboard, a piece of glass, or a piece of plastic, something else happened. You know, the force is going to change. The force is going to be a little bit smaller. Okay, and why is that? That's because these electric charges are creating a polarization in the material. That's what we call polarization. It creates a slight polarization in the material. The atoms are neutral, right? You have positive charge at the center of the atom, negative charges are surrounding the atom. When we put a dielectric plate right in here, the atoms of this dielectric plate becomes stretched, just like you see, and you see a separation of charges. This separation of charges acts against the force of between those two plates, and it's because of these separation charges that we end up with a different capacitance. Okay? Polarized molecules generate a small electric field within these molecules that cancels out the net electric field of the plates. Okay? So that's why we end up with a higher capacitance and less energy there inside the capacitor. Higher capacitance doesn't mean more energy, okay? It means less energy. So let's go ahead and continue here with our, here you go. We're gonna do the trial, right? We're gonna start with our first dielectric material. Go here, oh, don't forget to go here to our new table. Oh, what did I do? Here you go, copy and paste. Here you go. We will need, let's see if we need anything else. Separation plate, yeah. All we need is to put, I'm going to clear that. Let's see. Now I will clear this one. We keep the same separation. Yeah, let's keep the same area. Right, it's just the capacitance that's going to change because now we have, and then here you go, we're going to put our Kappa constant here at the top. Kappa equal Teflon, right? 2.1. What value did he put there? Yeah, 2.1. That's good. Don't forget this is Kappa. This is supposed to be a Greek letter. Here you go, Kappa. And I'm gonna make it nice too. In this case, in the first case, because it's the air, the Kappa was exactly equal to 1. Okay? A little bit more than 1. A little bit more than 1. We're going to repeat the same distances, keep the same area. What matters is the ratio here, A over D. Shrink. Here you go. We can disconnect the battery. Oh, we need to put the capacitance here. What else we need? Voltmeter. We don't need the voltmeter, do we? Yeah, we don't need the voltmeter. Let's see. Yeah, still 1.5, right? See, still 1.5. But the capacitance is going to be different. The amount of charge is going to be different as well. We can increase the separation. No, we cannot increase the separation. We can only decrease the separation, right? Okay, capacitance is 0.19 times 10 to minus 12. A 10 millimeter separation. .19 times 10 to minus 12. Okay, then we shrink it to 5, right? We did like that 5 before. Yep, 5. And capacity becomes 0.37. 10 to minus 12. Oh. 10 to minus 12. Then we increase to 6 millimeters. 0.31 times 10 to minus 12. Okay. Let's go to 7 millimeters. Okay, in this case, my dielectric material is changing its thickness, right? In real life, something like that doesn't happen. A thin block of dielectric material is not going to change its thickness, so you got to take it out and put another one in there with a different thickness. 0.26 times 10 to minus 12. We gotta go for 8.1 now. Yep, 8.1 right in here. 0.23 times 10 to minus 12. Let's compare the capacitance before and after. Wait a minute, the capacitance increased. Yeah, the capacitance increased. This capacitance here is higher than this capacitance, okay? 10 to minus 13 is higher than 10 to minus 14. Okay, just by inserting the dielectric there, the capacitance increases. Is the same distance, is the same area, is the same ratio. But the capacitance changes because we have a different dielectric material there. (8.1). Next, 8.9. 8.9. Whoa, yep. 0.21 times 10 to minus 12. Here you go. Next, 9.5. Here you go. 0.2 times 10 to minus 12. And the last one is 8.7. Separation, go back 8.7. Yep, 0.21 times 10 to minus 12. Here you go. Huh? Something wrong here? We got the same capacitance here. Interesting. Okay, maybe it's very small. The difference is very small. Yeah, it looks like we're unfortunate with the value here of the separation. Yeah, those two we see a difference, but not those two. See that? That's because we got too small of a difference. Let's use a different value here. Yeah, let's use a different. Instead of 8.7, let's use 7.5. Otherwise, we're going to have values too close to one another. 7.5. We have to redo without the 7.5. Here you go. 0.25 times 10 to minus 0.25 times 10 to minus 12. Let's see. Yeah, just slightly different from this one. And then we gotta do for the other one without the dielectric material, right? Let's okay, here you go. No dielectric material. Connect the battery. Let's make sure we have what we're supposed to be. Disconnect the battery. That's what we get for the capacitance. 0.12 times 10 to minus 12. Change it. Okay. That's what we did for Teflon. Now we're going to do for another material. We're going to do for paper, a block of paper. Let's reset it all. Yeah, costume, paper, good. 1.5 volts, good. Here you go, paper. Block. Make sure this is nicely aligned here, right? We're going to repeat what we did before. Copy this guy, paste it right in here. What is the 3.5? Now it's 3.5 kappa. (2.1), 3.5. We're going to use the same dimensions. All you have to do is to change the kappa. Clear contents. Go back to the simulation. Don't forget to, the capacitance must show up there. We don't need the voltmeter. Start at 10 millimeter separation, 0.31 times 10 to minus 12, 5 millimeter separation. 0.62 times 10 to minus 12, 6 millimeter separation. 5.51 minus 12, 7 millimeter separation. 0.44 times 10 to minus 12, 8.1 millimeter separation. Here you go. 0.38 times 10 to minus 12. What else? 8.9. Here you go. 0.35 times 10 to minus 12. Next, 9.5. 0.33 times 10 to minus 12, and we have 7.5. 0.42 times 10 to minus 12. Is that 3.5? Yes, right? Paper. And the last one should be glass. 4.7. Kappa is 4.7. Everything changes but the capacitance. Clear contents. By the way, let me show you something else. Let's see if that's what's supposed to do. If I displace, watch for the capacitance. If I displace here this guy, this dielectric material, see that? If I keep a the capacitor partially filled with the dielectric material, the capacitance change. Do you see that? And he even has the offset value of the dielectric material. Okay? So keep that in mind. We can also have a different capacitance if you have only part of the dielectric, only a fraction of the dielectric there inserted. No dielectric, right? The capacitance is minimal. We keep on inserting the dielectric, the capacitance keep on increasing little by little. See that? So there are three ways of changing the capacitance. Oh, actually there are four ways of changing the capacitance, right? By plate separation, plate area that we didn't do. Let's see. It doesn't change the area. Interesting. Oh yeah, here you go. I can change the area finally, right? We can insert different dielectrics, and then we can change the offset of the dielectric. So there are four different ways of changing the capacitance of a capacitor. If I take it completely, right, it's as though you have air or vacuum there within the capacitor. Let's insert it back. We are not going to do anything with the offset of the dielectric. 0.42 times 10 to 12. Again, the capacitance is 4.7 now. 0.42 times 10 to minus 12. 5 millimeters, the smallest possible. Here you go. 0.83 times 10 to minus 12. What's next? 6 millimeters. Let's go for 6 millimeters. 0.69 times 10 to minus 12. 7 millimeters. Here you go. 0.59 times 10 to minus 12. Now I'm going to 7.5, okay? So I don't need to return here. 7.5, let's see if I can get it. Yeah, 0.56, 10 to minus 12. Oh, wait a minute. Right here at the bottom. I'm doing of 7.5, so I have to log right in here, right? Next is going to be 8.1. Here you go. 8.1 is 0.52 times 10 to minus 12. Next, 8.9. .47 times 10 to minus 12. And the next one is 9.5. Here you go. 0.44 times 10 to minus 12. So we got everything. We are going to put everything bold-faced here so it looks nicer. And let's go here to our notes, handouts. Now add a voltmeter, and plate charge meter, and the electric detector. Keeping the separation of the plate area the same. Play with several different dielectric materials since notes how each measurable quantity changes. Okay, so just play. It doesn't tell you to do. Plate charge meter and the electric field detector. So voltmeter, plate charge. Okay, plate charge. What else? He asked for electric field detector. Wait a minute. How do you want me to play it? And the electric field detector. If field detector grayed out in the simulation. Yeah, if it's grayed out, you cannot do anything about that. I do not know why it's grayed out. If you folks can figure out how to allow that to, let's see, electric field line. Yeah, see, we cannot do much about that, right? But at least the plate charge is a measure of the charges, right? If I withdraw this guy, the amount of charge decreases. Okay. Oh, that's all. It doesn't want you to take any measurement at all. Now add the voltmeter and the plate charge meter, keeping the separation of the plate area the same. In the play with several dielectric materials. Let's see. Okay, that's one dielectric material. That's another dielectric material. Less charge. Let's go, Teflon, right? Less charge. It should decrease the amount of charge. Okay? 0.14 to 0.29. 0.14 should increase the amount of charge. 0.14 to 0.29. So next one, or increase the dielectric constant again. 0.29 went to 0.49. Glass, 0.66, right? So here you go. Teflon, 0.29. Paper, 0.49. Glass, 0.66. So the amount of charge increases as you change the dielectric constant there. But not, what about the voltage? What about the voltage? Okay? Take it out, the voltage remains the same. See that? But what if we disconnect the battery? Let's see if it changes anything. Yeah, if you disconnect the battery, then the voltage is gonna change. Okay? See, it goes with the dielectric is 1.5 volts. Without the dielectric, it increases the amount of charge. It's whether you keep the battery connected or not. Okay? It makes a difference. Why is that? It makes well, it's simple, right? The battery, connect the battery. The battery is ensuring that the potential difference remains 1.5 volts no matter what. The difference of potential between the plates remains the same no matter what. And because of that, it will affect the amount of charges in the plates. Now, if we disconnect the battery, then the potential difference, the energy between the plates, is going to change. Because there is nothing holding it constant, okay? In this case, it increases when I take out my block of dielectric material. Let's put a different dielectric material now. 1.5. We're going to put, instead of glass, we're going to put paper now. Yeah. Increase the voltage. We're going to put Teflon now. The lower the dielectric constant, the higher the voltage whenever the plates are connected. What about the charges? The charges remain the same. And the capacitance change as well. It's just, so let's, now he's going to ask you to plot the graph. Here's just, qualitative. Using Excel or the program of your choice, plot plate area separation where plate area divided by separation versus capacitance. Well, okay, what he means here, yeah, what he meant here is we usually say capacitance versus area separation, okay? But what comes first, and that's what goes in the y-axis. Here he's just emphasizing let's plot it. Capacitance in the y, the ratio in the x. Here you go. This ratio here in the x. Insert. Here you go. We must have three graphs, three different graphs. I don't need that. See, it's a straight line, just like we saw in the equation. We do that as well. For this one, insert. Don't forget to work out on the graph with the labels and everything, right? I'm going to, we have to optimize the space. I'm going to put between 9 and what? 9 and 21. Let's see if it's 9 and 21 is a good one. Yeah, 9 and 21 is a good one. Now what about in the vertical? The vertical axis from 8 to 1.8. 8 minus 13. What happened here? I had done something wrong. Yeah, let's see. I'm still working on the first graph, right? I'm optimizing the first graph. 8 times to 10, okay. 8 times 10 to minus 14. 8 minus 14. Can I do better? 1.8 minus 13. Instead of 2, we gotta put 1.8. Okay? Optimize the space. Put the labels here. You do not need to have all those zeros here. I want you to adjust as well. Do that, figure out on your own how to do that, right? We don't need to put 2 decimal places here in the y-axis. Here too, you don't need to put 2 decimal places in the y-axis. Insert. Insert chart. I'm not going to adjust this graph. You do that on your own later on, okay? Otherwise, you're going to spend too much time doing that. But you gotta make sure that you optimize the space. The last one. Oh, I didn't plot everything. 1, 2, 3, yeah. Good, we got it. This one as well. Insert. Zoom out so we can try to see everything here. What else do we need? We need to put the equation there. Right click, add trend line, display equation chart. It's gonna be linear. Here you go. I'm gonna put some more decimal places there. Format trend line label, general, scientific 2. Good. 8.78 times 10 to minus 15. Don't forget the units. Here's the same thing. Add trend line. Here you go. Format trend line label. We're gonna put in scientific format. Good. 1.8 times 10 to minus 14. It has a steeper curve. What about this one? Add trend line, display equation chart. Yeah. Format trend line label, blah, blah, scientific. What's going on here? Huh, why I did text? I meant scientific. Go one more. 4 graphs. Scientific. Here you go. Let's see what else he asks. We got our 4 graphs. What do you think our equation represents? How do the equations change depending on the dielectric? Do, he meant do, right? How do the equations change depending on the dielectric? Right? Which dielectric is the higher? Let's take a look. Let's take a look. Okay, dielectric is increasing from the left to the right. What's happening to the slope? The slope is increasing, right? Increase here, almost, no, it didn't double. It is increasing. The slope is increasing with the dielectric, which is expected, right? And this slope, if you go back to the equation, what is this slope? Go back here to the equation. This slope is given by this parameter right here, kappa epsilon naught. This is being plotted in the x-axis, so that must be the slope, kappa epsilon naught. Okay? The epsilon naught doesn't change. If kappa increases, the slope must increase as well. Next, how do the plate affect capacitance? Okay, just look at the equation. Increase the area, you increase the capacitance. Increase the separation, you decrease the capacitance. Okay, so just take a look right in here. Here is A over D. As A over D increases, the capacitance increases. What does it mean? It means that if the area increases, capacitance increases. If the distance increases, the capacitance decreases. That's what it means. 343. Man, we'll be able to do only one lab today, huh? From play with different dielectric, explain how you think a dielectric affects the capacitance and the electric field, okay? What purpose do you think a dielectric might serve? I don't want to do the second part because we still didn't cover that. I think it's too premature, you know, to start covering things that we didn't cover, things in the lab that we didn't cover in the lecture. Okay, so let me see. 3:44. We have half an hour to go. Any questions? Okay, so go ahead, do your lab report only for part 1. Here you go. I'm gonna, for the lab report, you do not need to do the last part. You do not have to do. You don't need to do part 2. However, after we cover circuits with capacitors, go back to the simulation and play with it on your own. Play with it on your own, okay? So you can understand better how combination capacitors work. No need to do conclusions either. Okay, so let me save this guy here. And any questions? So let me tell you what I'm gonna do in the next few days. 1, exam tomorrow. So I'm gonna spend the rest of the day preparing your exam. I will prepare your exam today. Prepare your exam today. I'm gonna make the exam available 9 a.m. tomorrow. Is that okay? I'm going to make the exam available at 9 a.m. tomorrow. You will have from 9 a.m. tomorrow. Is that Thursday? Yeah. To 8:59 a.m. And let's put 9 a.m. too. Friday to do the exam. Once you start the exam, you must finish it in 1 hour and 15 minutes. Okay? You cannot start the exam, pause, come back later on. No, you cannot do that. You have 1 hour and 15 minutes to do the exam once you start it. But you have a window. Everybody can do that tomorrow? Do we have any important Any important meeting that you have to attend? Let me go through one by one for you folks, so you don't have any problems here. Bella, can you do the exam tomorrow, Bella?
Yes, it's open all.
What do you say?
You could do it anytime within tomorrow.
Yeah, 9 a.m. to 9 p.m. But once you start, you gotta finish it in 1 hour 15 minutes.
All right,
You cannot break it down in small breaks, okay?
Thank you.
Okay, so no problem, right, Bella? Annabella, can you do the exam tomorrow?
Yes.
Okay, Sarah?
Yes.
Okay, Carly?
Yes.
Okay, Mahedi?
So just 9 a.m. tomorrow to 9 a.m. Friday, right?
Yeah, so you pick up 1 hour and 15 minutes in this time, in this 24-hour window.
Okay, perfect.
Okay, so let's write this way. Pick up, you must pick up a 1 hour and 50 minutes window within this 24 hours time. Okay, that Mahedi, yes, you can do that. Wesley, can you do that? Can you do that?
Yeah, for sure.
Okay, Ada.
Yes.
Okay, Jordan,
Yes.
Donica. Hello,
Yes,
Donica. Yeah.
Yes.
Okay, good. Shagar,
Yeah.
Daniela,
Yes.
Dior,
Yes.
Shreya,
Yep.
Peter. Are you there, Peter? Might be training one of his customers. Let's see. I see him. Okay, no answer. I'm gonna put here no answer. Okay, Anna,
Yes.
Kaylee,
Yes.
Alisa.
Yeah.
Okay, Jasmine.
Yes.
Okay, good. So everybody can do that. Now, what else? I'm going to prepare. I'm going to prepare homework for chapter 15, right? As well. So I have a busy day today. What else I'm gonna do? I'm going to prepare the video for chapter 15. Okay. Lecture video. I'm going to prepare the lecture video for chapter 15. I'm going to prepare homework. Okay. Lecture video for chapter 16. I already have some of that, okay? There you go. A new lecture video for chapter 16 will be combined with the lab video, right? Lab video for lab 2, no, for lab 2, no, for lab 3, right? For lab 3. Here you go. Don't forget, there will be the lecture video for chapter 16, and which must be combined with the lab video for handout 3. Handout 3, let's get this syllabus here. Handout 3, yeah, Coulomb's law. So I'm going to start working on that as well. Exam 2 will be on July 29. It's going to be at least chapters 15 and chapter 16, and will be at least chapters 15 and 16. Okay, what else? I'm going to prepare homework for chapters 15 and 16. Okay? Let's see how it goes if you have time to cover chapter 17 as well. So, exam 1, let's see here. I'm going to prepare homework chapter 2. I'm going to prepare a new exam 2. Exam tomorrow. Exam 1 tomorrow. I prepare exam today. Chapters. What's going to be the chapters? 13. Tomorrow will be on chapters 13 and 14. I'll prepare the exam today. I'll make it available at 9 a.m. tomorrow. You have from 9 a.m. Thursday to 9 a.m. Friday to do the exam. Once you start the exam, you must finish it 1 hour and 15 minutes. You must pick up a 1 hour 15 minute window within this 24 hours time. Okay, so that's 3:53. Okay, so that's what we have for today. Any questions? I will save this document as a PDF and upload there in your folder. Also, I will upload the video there in your folder, okay? So if you don't have any questions, we can stop now, and I see you next week.